Okay, this second video will probably deal with something even more common for you as you do research or read research reports, and it's going to be dealing with comparing two populations. So this is just something I took from the textbook for you to see. So you have your null hypothesis right here, H sub 0 or H naught. They call this the null hypothesis. And the null hypothesis always has the equal sign saying that this is the mean of this is equal to the mean of this. So the mean of maybe sample T is equal to the mean of sample C, or the mean of population T is equal to the mean of population C. The null hypothesis says that it's equal. There's an equivalency here. Whereas an alternate hypothesis is you saying that there is a difference, that they are not equal, that there's something about the mean of T that makes it different from the mean of C. You can replace these equal signs with less than and greater than signs, but the equal sign always has to be in the null hypothesis, and a equal sign should never be in the alternate. So traditional hypothesis testing research says that the null hypothesis is that there's nothing going on, or it's greater than or equal to, or it's less than or equal to. Notice the equal sign is always in the null hypothesis, and then the alternate, H1, the not equal sign. So they're not equal, or it's just less than, or it's just greater than. All right. So in researching, my experience is that t-testing is far more common, since the true population variance of whatever the big population is often unknown. And again, when you do t-testing, it assumes a normal distribution, although I believe that that normal assumption is routinely violated. You should remember that you can do a normality test very easily just by using the Shapiro-Wilk test or that S. Francia test. And then when you have a p-value that's really low, it suggests a significant difference from normality. So these comparisons of two distributions, you can do t-test or z-test, and the focus is on the means. The z-test should never be used when you have less than 30 samples. And again, though, in reality, I see the t-test often used even for larger samples, mainly because the true population variance is often unknown. In order to do this in Stata, to compare population A versus population B, or to compare the average of sample A versus sample B, the data need to be organized in at least two columns, and then you can tweak how you organize those columns here in a minute. So data can be in one column with a second column as a group, or the data can be in two columns like so. So you could have the data for something like we're comparing E. coli densities in Lake Reba versus Will Green Lake. So you might actually have two columns of data. This is the variable EC underscore LR. This is the variable EC underscore WL. So the data are in two columns. So that's one way of doing it. The other way is you could have a code. So you have all the E. coli data in the left, and then you have a variable like lake name, and then it's LR, 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 and then down here, these are the Will Green Lake ones, WL. You could also change this to being Lake Reba, like Lake Reba, and then coding these as 1, 1, 1, 1, 1, and then Will Green Lake not being Lake Reba as being 0, 0, 0, 0, 0, 0. That's just a couple ways of doing it. So data can be organized in two columns, like so, or they can be organized in two columns where all the continuous data are on the left side, and then your variable name or your code is on the right. So again, you can also code it as ones and zeros. So ones being the Lake Reba samples, 0 being the Will Green Lake samples. Now, you can do t-testing by typing in the commands, or we can use Stata using the click pushing, using the mouse and clicking what you need. One thing we might be interested in, I'll do an applied example using the data set that you are familiar with. We could compare drug overdose rates for the heavy rural counties of the United States versus the rest of America. And we'll call heavy rural greater than 90% rural, and the rest of America being 90% or less. So we can get the mean overdose rate. So what's the average number of overdoses per 100,000 in rural American counties versus the average overdose rate in other American counties. And the null hypothesis says that they're equal. There's no difference. That the average for rural America is equal to the average for the rest of America. So there's no significant difference. They're equal. Whereas the alternate says, no, we think something's going on. Rural America is different from the rest of America. You could make this greater than or less than or equal to based upon what your hypothesis is. In order to do this in Stata with that one data set, we need to create a variable to call rural America rural, yes or no. So we can use these commands. I could generate the variable rural equals 1 if rural percent is greater than 90. All right, and then you hit that and it'll run, and then you type in replace rural equals 0 if the rural percent is less than or equal to 90, and then it'll code every county in the United States as 0 or 1, 1 being the ones that are the most rural, 0 being the ones that are less than 90% rural. All right, easy enough. So that you code the data. I can go back. You can see how right there in Stata, that's what it looks like. So I don't really need to open Stata to show you that. So now we can go to Statistics, Summaries, Classic Tests of Hypotheses, and then we select t-test, mean comparison test. So we have some different options. We could do the one sample t-test where we already know the national average, which we don't. So it's probably better just use the two sample using groups. So our two groups, we have two groups. It's going to prompt us once we click on that. It's going to ask for some more information below. So since we have a group column for rural 0 and 1, we choose two samples using groups. And then we go down here to the mean comparison test. This is the two sample test, but the variable name is drug overdose rate or mortality rate, whatever. And then I click on the group variable name, which was that new one we created. Remember, we created one called rural. So we created that. It's right there. If you don't know whether the variances are equal or not, check unequal variances because that's more conservative. You'll err on the side of caution. So you check that, and then you hit OK. So it's going to do a t-test on drug overdose rates by rural. There's the command. By hitting OK, you see the Stata command. It actually typed it out. The t-test, drug overdose mortality rate by rural, unequal. So you can reuse this. You could copy and paste this command and get rid of drug overdose mortality rate and do something else like obesity rate or life expectancy or whatever you want. So what did we get for our output? So we see for group 0, the non-heavy rural, and pretty much the rest of America, we had 1,556 observations. We only had 69 rural counties in America. There are over 3,000 counties in the United States, so we lost a lot of counties. We lost a whole lot because of maybe suppressed data, not enough cases in that county, that it didn't have data on overdose rates for a lot of rural counties. So we see the observations being 69, the mean for those rural counties being 27.9 deaths per 100,000 versus 17.7 for the rest of the United States. If you go down is there a difference? So is there a statistically significant difference? And it's saying that there is a statistically difference. It means that, among these rural counties, well, comparing the group 0, the mean of 17.7 is statistically different at the 0.025 level, meaning that there's less than um, the number of cases in this group than there are in rural America. And then this is a simple one. Are they different? Yes or no? And we see a p-value again of 0.0000000. So the hypothesis for any difference, we would report it as, since p is less than 0.001, because that's impossible. You can't have 0.0000. So it's always reported as 0.001. So yes, there is a significant difference. And then is rural America greater than the rest of America? And the p-value there is 1.000, or pretty much greater than 0.99999. So no reason to believe that it's greater than. It's obviously significantly higher. This group 1 is significantly higher than group 0. There's a significant difference here. So you can just see that intuitively. 27.9 versus 17.7. Rural America is high, obviously higher at first glance, but you have the statistically significant results that back it up. All right, so again, you can copy and paste this for something like life expectancy. This is the one for life expectancy. So urban and the rest of America versus rural America, they're kind of close, 0.83, 77.72. When we look here across the board, no statistically significant differences. This one's above 0.05, this one's above 0.025, this one's above 0.025. So is there a difference between rural and non-rural U.S. life expectancies? We have insufficient evidence to conclude that there is, so we accept the null hypothesis that there's no difference. So easy enough. So what about when the data are organized in 2 columns? So maybe you've went into Stata and created 2 columns of data. You only had 5 samples from E. coli from Lake Reba, 5 from Will Green Lake. You punch them in there. So you've got these numbers. You want to see, is the E. coli level in Lake Reba significantly different than the E. coli levels in Will Green Lake across the 5 samples that you collected. So you punch them in Stata and they look like this. And then instead of selecting on using groups, we actually have them in 2 separate variables, E. coli LR and E. coli WL. So we have these 2 variable names. We can again assume unequal variance because we don't know. So if unknown or unequal, we click it. And then what do we get? We get the mean for E. coli for Lake Reba at 80.26, the mean at Will Green Lake 60. We don't have a lot of samples, so we have large standard deviations, large errors. So it makes it hard to see a statistically significant, finding. So small sample sizes make it hard to see a significant difference. We don't have enough statistical power. More samples would be required. But here, 0.66, well, is there a significant difference there? 0.66? Well, since 0.66 is higher than 0.05, we have to conclude no significant difference. So that concludes this part on 2 sample means testing, and we'll move on to the next part here shortly.